Okay, so let's take a look at an example of setting up a voltage line regulator. And we have a scenario right now where what we have is we have a 12.47 kV circuit. And so just kind of show you what this would look like. Let's just kind of jump to this next slide. Basically, I've got a substation, and then I've got two different feeder segments. The first feeder segment has residential distributed load. So this load's kind of uniformly distributed up and down the length of the segment. It's going to be 2 miles. They have a second segment's 2 miles where all the load is just at the end. So this is on the right, what's called spot load, all the loads in one place. Distributed load is where it's just uniformly distributed up and down the feeder. We'll put a regulator in the circuit, and we'll have a couple buses. We'll have a bus A and a bus B. And if I put that line regulator in the circuit, what that's going to do, that's going to create a new bus. I would call that bus A primed. And so the substation has some voltage regulation as well, but we won't be too concerned about that. We're just going to assume it's at some sort of a set point, right? So if you look at the problem statement on that first segment, we've got 3,000 kVA of uniformly distributed load. It's at a power factor of 0.9 lagging. The industrial spot load is 3,000 kVA at 0.9 power factor lagging. And then the line elements are going to assume to consist of 4-aught conductors. Now, if we had all the construction information, we could figure out all the impedances and everything. But let's just assume that we've done all that work and we found out that the positive sequence impedance is 0.592 ohms per mile for the real part and 0.761 ohms per mile for the reactive part. So let's suppose we had this circuit operating. We'll start off with a baseline, and we've gotten some complaints from this industrial customer that the voltage is too low. And so what we're going to do is we're going to fix that by putting in this regulator. And let's suppose the regulator is going to consist of 32 steps. So that means we're going to have 16 physical taps. So the 32 again refers to the plus minus range operation. 16 taps is the number of taps we have on the series winding. And let's suppose this gives us plus or minus 10% regulation. We'll assume the substation is set to 1.04. So we have 1.04 per unit here. And what this would correspond to on a 120 volt base would be 124.8 volts. So I want to come up with, once we've done the baseline, and we're going to add this regulator, I want to come up with the control settings for this voltage regulator. And what we're going to want to do is we're going to want to make sure that we can keep this voltage at the industrial customer as close as we can to 1 per unit. So the whole idea would be to basically make this be the goal. We want to get 1.0 here regardless of what the loading condition is. The other thing, we want to make sure that we don't drop the feeder voltage too low. So we want to make sure we don't drop the feeder voltage below 0.975 per unit. And we want to make sure that our maximum customer voltage anywhere in the circuit doesn't get any higher than 1.04. So I've got a maximum limit, I've got a minimum limit that I want to try to maintain on the circuit. The way I'm going to analyze this, I'm going to go ahead and just assume that we can neglect the bandwidth effects and just assume bandwidth is 0 volts, and that'll kind of help us in our analysis. We'll also assume that this voltage regulator has a current rating of 200 amps on the load side, and that the CT primary current rating is going to be 200 amps. All right. So we'll do a baseline calculation for what the voltage drop was before we put the regulator in the circuit. And then what we're going to do is we're going to figure out what's going to be the voltage band center setting, what's going to be R set and X set for the line drop compensation. We're going to check the maximum and minimum voltage, and we're going to figure out what's going to be this tap position at peak. The other thing to keep in mind, as far as the operation of this circuit, is we're just doing this calculation right here at the peak condition, but keep in mind the way the low would actually look is a low would actually have, some type of peak during the day, and the other times we're going to actually be below that value. But typically, if we're below that peak value, we're generally going to be within range. But anyway, we're just keep in mind, even though we're doing the calculations for the peak, what this line drop compensation allows us to do is basically to make sure we have that voltage regulated right at that customer. That's the beauty of having the line drop compensation. So to do the baseline, what we're going to do is we're going to calculate the K factor. We're going to calculate the K factor assuming these line constants, and we're using that power factor of 0.9. Recall that when we normalize by voltage, this is a per phase calculation, and so we divide through by the line to neutral nominal voltage. We're for a 12,470 kV circuit, this would be the 12,470 divided by square root of 3, which is 7,200. And we always do this at nominal. So if you were going to get a new value voltage based on this, we don't correct this. We don't do this iteratively. This is always going to be at nominal. And again, what we're doing is we're linearizing around nominal voltage. We're kind of doing a constant current load calculation. So anyway, what I'm going to do in this case is I'm going to get this K factor, and this is going to have units of percent voltage drop per kVA mile, and it's going to have a value 5.559 times 10 to the minus fourth. Once I've got this K factor, then what I do is I multiply this by the line length, and I also post multiply this by the net load. Now you'll note in this case that I've got the two different loads on this first part of the circuit. I've got the load component due to the industrial load that's flowing from the substation. Okay, there's the industrial load part, but I've also got the local distributed load to consider on here as well. So there's two different load components. Note that in this case that as far as the net load, I've got whatever's below, which is the industrial load in this case, and then whatever's on that line segment, which is this 3,000 kVA of distributed load, which I have to divide through by a factor of 2 because it's distributed. And so this gives me a drop in the first section of about 5%. Now in the second section, all I need to do is factor in just the industry load. And so again, it's got a line length of 2. I've got the K factor in here, and it's going to give me a voltage drop of 3.335%. And so the net voltage drop I have going from the substation down to that end industrial customer is going to be 8.338%. And then if I were to take the 1.04 at the substation, subtract off the 8.338%, this gives me 95.66% of the rated voltage, which is going to be below what I generally try to get for the primary drop, not going below the 97.5% limit. Because you have to keep in mind that, and when you get to the customer, there's some transformer drop as well, right? And so we have to take that into account. So we're a little bit on the low side. We got to boost this voltage up. So now that I kind of know the extent of the problem, and I know that if I have loading on that, full loading on that second feeder segment, I get a 3.335% drop, then I could start looking at the settings. So what I'm going to be doing for the regulator set point is I'm just going to be setting that to 120 volts because I got the line drop compensation. And so if I want to have 1 per unit at the customer, if I have line drop compensation clicked on, then I just simply put my target voltage into the controller. Now, what's going to happen is if I'm at a full load condition, then what's the regulator output actually going to be? Well, what's going to happen is that regulator is going to measure the current. It's going to apply RSET and XSET, which is going to emulate the voltage drop. So basically what the regulator is going to have for an output is going to be the 1 per unit target plus the drop across that line segment where that regulator is actually going to output 1.034 per unit volts when I'm under a full load type of condition. So this is going to be below my upper threshold, and I'm still okay in this case, but this would be one check that I would probably need to just take a look at. All right. So now I got to come up with the settings for R and X. And again, I have to take into account that it's not just simply the actual resistance in this case. What I need to do is I need to convert that to units of voltage. So if I have the line resistance, for example, per mile, I multiply by the total number of miles. This is net resistance. The CT ratio is 200, and then what I need to do is I need to divide that by the turns ratio. And if this is a 12.47 kV circuit, that's 7,200 volts line to neutral. I need to convert that to 120 volts for the control circuit, which gives me a ratio of 60. All right, so what I've got here in the denominator is this ratio of 60. That's N for the PT. That's what the PT is doing for the control circuit. So this gives me effective resistance setting of 3.94 volts. It gives me effective reactance setting of 5.08 volts. The next thing I'm going to do on here is I'm going to check maximum, see what the maximum value on the circuit's going to be. I already said that at the regulator, we got 1.034. The other place it could be high would be at the substation then, because voltage is always going to drop as I go away from the regulators. And so the worst case voltage on the circuit is just simply going to be 1.04, where I'm okay in this situation right here. If I'm looking at low voltage, this is a little bit tricky. If I'm looking at low voltage now, where can low voltage happen now in the circuit? Because I'm already kind of boosting voltage for my industrial customer, where the other spot I could have a low voltage is going from the substation to the source side of that regulator. So I have to check what's the voltage drop across here. And so when I do that particular calculation, I take the substation, I subtract off the voltage drop under full load for that first section, which is going to be at 0.99 per unit. And I'm okay in this particular scenario because this is above my 0.975 limit. All right. So I've just double checked different places in the circuit, make sure my maximum voltages are within range, my minimum voltages are within range. One other thing I could do is I could also check to see what my tap position is. So I got 1.034 coming out of the regulator. I've got 0.99 going in. The boost that I get is going to be the source voltage times 0.1. This corresponds to the 10% winding I'm using, times the tap position divided by 16. And so I could use this to solve for the tap position, and the tap position is going to be 7.11. Now you can't have a floating point number for the tap. It has to be an integer. And so, you could see what you'd have to do in this case is like round to the nearest integer tap position. Now, if you want to check this in Windmill, you can do all these calculations in Windmill as well. And so I basically set up the same type of a circuit where I have the overhead and I have the two sections, and I've got the regulator in the circuit, and I've got the load model in here as well as the source. And what I'm doing for the voltage drop calculations is I'm setting this up where the base voltage is going to be 120 volts instead of 7,200. That just makes it easier to check against my limits. The other thing you may want to play around with in here is you might want to play around with the tolerance a little bit. And the other thing I'm doing is I'm using a balanced analysis, because when I did this by hand with the K factors, that assumes everything's balanced. So I'm really doing a per phase balanced analysis. And so I would check this option for my voltage drop analysis. You go in and you could set up the regulator model, and this is also posted up on the Moodle site. So I've got a 7200 volt single phase regulator in this case. I've got the CT rating in here. I got the current rating. I've got the percent boost. I have the number of steps, and the incremental change per step is the 10% divided by 16, which is 0.625. I could also plug the bandwidth in here as well. So what MillSoft's going to do and what Windmill is going to do, it's going to apply these parameters in doing the simulation. Then, when you're setting this up, you also would select like the YY ground, and you would basically set this up where you have all phases the same. So I have 3 single phase regulators in here, and each single phase is operating exactly the same way. Here's my definition that I'm linking to from my equipment database. So this is in the equipment database here, EQDB. This is in my model, and note that what I'm doing in this case is this is my target voltage of 120 volts, and I have my voltage set points for the real and the reactive part of the line drop compensation. You could put a first house high in here if you want to, and then you could also put they actually have something called a first house low, where you don't want the voltage to go below a certain point. We didn't really use these, but you can actually put these into the control as well. And if you want to take this out of the circuit, you could bypass it then. So once you have that set up, you have to set up the line models. What I'm doing for the first part of the line model is I'm actually putting this in by phase. And so I'm actually selecting a 4-aught conductor with a 1-aught neutral in here. What MillSoft's going to do is going to go through and calculate the impedances. This was actually selected before where I didn't have it transposed. And so it's showing the actual values you're going to get in here for ZAB and C in this particular case. And then for the second overhead segment, what I'm doing is I'm entering these models a little bit differently. So what I'm using in this case for entering these particular values in, and you can't see the left-hand side of this, but there's actually what's called a ZSM model, where what I'm doing in this particular case is I'm entering in the positive sequence values directly, where the positive sequence values are 0.592 plus J 0.761 ohms per mile. And so you could actually then enter this in directly if you want, and then just make sure I have the distance that corresponds to 2 miles. So what this basically does is it takes what you get out of the line parameter calculations and allows you to put in values for Z1 and Z0 in directly. So once I have all these entered in, then I can run the power flow. I'm doing balanced voltage drop analysis in this case. And then what you'll actually see is what's going on in the circuit. You see indeed that we're keeping the voltage pretty close to 120. The tap position in this case is actually 8. It actually rounded up instead of rounding down. And because it rounded up, then the voltage at the load's actually a little bit higher. And there's actually a setting you could use in MillSoft where you allow this to be a floating point number, but I just thought I'd leave it here as an integer so you could just see what the difference would be between the two types of analysis. So what this basically, you could see from this is we get about the same analysis results using Windmill as we would have doing this by hand. The other thing you could do within Windmill is you could also show the voltage profile. And so what this shows, you're at the substation, you go down the feeder, the voltage drops down, then you get to the regulator, you could boost it back up, and then you go back down the second line, the voltage drops back down again until you get to the load. And you can see that because you actually do have slight differences between the phase impedances in here, that you actually do get a little bit of difference between a phase A and B and a C phase voltage in this case. So anyway, that's a simple example to kind of show you how the voltage line regulator works. And then we'll be combining this with capacitors later on, so you can kind of see how the two could be used for actually solving voltage drop issues. As far as some references, if you're looking for some other references, Tom Short in his book does a pretty good job of talking about the construction of the regulator and kind of how you would make use of it. And then if you want to see more on the details of the modeling, you could take a look at Bill Kirsting's book. Okay, so that's all I've got for the regulation. And what we'll be doing in the next lecture is we'll talk about how the power flow actually gets calculated then.